In the previous video, I managed to mount all 3 rollers along with their attachment mechanism onto the backbone, which allowed me to run a first test. Things looked promising until the machine in progress began to shake like a washing machine with a brick in it once it passed 3000 RPM. So before proceeding any further with the build, it's time to sort out a few final details. One of those critical points is the balance of the drive wheel. I actually made a short video on this very topic 2 years ago, titled A Balancing Intermezzo. If you're curious, do have a look at that. It's a real thriller. Here, however, I'll keep things simple. The method: let the drive wheel spin freely on 2 tiny ball bearings stripped of their grease in an ultrasonic cleaner. The bearings are lubricated with a bit of petroleum. After balancing the wheel with a dab of adhesive putty, I weighed the putty, a modest 750 milligrams. Not much you might think, but at 7,000 RPM, that tiny blob causes oscillating forces of about 2 kilogram force at 117 Hz, which, as you understand, is entirely unacceptable. The solution? A bit of precision drilling. It's straightforward to calculate how much material needs to be removed on the opposite side of the imbalance. In this case, 2 5mm holes, each 6.11mm deep, right into the steel hub at a radius of 20mm. We will see later if that did the trick. A second test I want to carry out is to determine under what tension I should mount a sanding belt, enough to ensure a nice tight and stable run, but not so much that it overburdens the belt or the bearings. Strangely enough, I couldn't find any relevant data on this from any sanding belt manufacturer. Odd, isn't it? I also want to find out how much the belt stretches when tensioned. This is where my small hydraulic press comes in handy again, because I built an accessory for it that allows me to apply tensile loads. With a bit of imagination, some steel discs, a strangely mounted micrometer, and a digital force gauge, I cobble together something unusual but good enough to give me a reasonably clear picture. The digital pressure gauge shows me the pressure in the hydraulic cylinder, and the force gauge, as well as it can, shows me the pulling force in kilogram force. The micrometer then lets me see how much the belt stretches in the center under that force. Step by step, I increase the pulling force and record the corresponding deformation. Using a telescoping gauge, I also measure the total elongation of the belt at each force level. Everything is neatly noted down. And finally, I push the sanding belt to its limit until it snaps. That turns out to happen at just under 30 bar, with a piston surface of 17 square centimeters that translates to roughly 500 kilogram force. Due to the lever system I'm using, I have to have that, so about 250 kilo of actual tension before the belt breaks. I'm sure the value varies between brands, but still, it's more than I expected. So I reckon that applying 10 to 15% of that force should be well within the safe range. The bearings can easily handle that kind of load, even at 7,000 RPM. Here's the graph of the measurement results. It shows that, with a central deflection of 2 to 3 millimeters and a pulling force of around 10 newtons, I'm right where I want to be. Great! That's one more question answered. Back to the build. I'm starting from the bottom with the base. This steel plate measures 200 by 200 millimeters. It's milled square with clean edges, and I add a neat chamfer all around. Later on, I'll smooth the surface and maybe give it a coat of matte black paint. Or not. We'll see. Using a black marker, I've marked the holes to be drilled. Even though my DRO allows me to position holes with high precision, I still like seeing the drawn lines and hole locations. It gives me a bit of peace of mind, just a way to double check that I haven't made some silly mistake in the layout. The holes are countersunk so that 6 M5 socket head bolts can later fasten this base firmly to the backbone and its support plates. If there's one home-built machine I've really grown to appreciate, it's this trusty little bandsaw. This small beast cuts through steel like it's having breakfast, no complaints, no fuss. Right now, I'm using it to cut the parts I need for the next stage of the build. Among them, the 2 gusset plates that, together with the base plate, will give the backbone a solid and stable foundation. The front gusset plate gets a beveled edge that, hopefully, will guide the grinding debris straight into the catch bin beneath the large roller. The rear plate gets a hole for hooking up the shop vac. And this angled edge, it serves no purpose whatsoever. I just thought it looked nicer that way. Here I'm making a support plate from mild steel for the rear side of the sanding belt. It gets a hefty bevel on both the top and bottom edges, allowing the plate to sit close to the wheels. 2 solid steel blocks make sure the plate can be firmly mounted to the backbone. Each block gets 3 set screws, so the support plate can be aligned perfectly square during final assembly. I drilled 2 countersunk holes in the plate for tension bolts that will pull it snugly against the set screws. I make sure there is enough space around for the bolt heads, so they don't interfere with the plate's ability to tilt. It needs to stay free to pivot. Mild steel, of course, isn't exactly known for its wear resistance. That's why I glue a spring steel facing onto it, which, if needed, can be easily replaced. The adhesive I'm using holds with about 8 tons of force on this surface area and can withstand temperatures up to 250 degrees Celsius before letting go. I wrecked my counterbore drill for M6 cap screws by running it straight into the top of a broken tap. Here I'm regrinding the tips of the 4 flutes using my tiny tool grinder. With a bit of luck, the drill will be usable again after this. Not exactly a beautiful chip, but the hole looks clean enough. Some kind of enclosure is needed to keep grinding debris, especially at high RPM, from being flung across the entire workshop. I'm cutting and shaping some aluminum sheet into strips that will form the walls. The front top strip gets a beveled section to leave enough clearance for the roller behind it. The holes are drilled, countersunk, and tapped in both the aluminum and the backbone for the M3 screws that will hold the strips in place. In a review I published earlier about the Proxon F500, I pointed out that getting the machine's head precisely vertical is nearly impossible because the head twists slightly when you tighten the clamping bolt. That's why the head has been locked in a carefully aligned vertical position for years now, after quite a bit of fiddling. But in that position, the FF500 can't reach the screw holes at the top of the backbone. Luckily, I can use the tiny drill and milling machine I built a few months ago. That does this job just fine. All right, time to temporarily assemble the machine and run a few tests. The footage pretty much speaks for itself, so time for some music. Using the small hydraulic press I built in the previous video series, I bend two 5mm thick strips into a nice tight right angle. They'll soon connect the controller housing to the backbone. One major issue is grinding dust. Those big, ridiculously expensive belt grinders that bladesmiths love so much are notorious workshop polluters, blasting abrasive dust all over the place. My workshop is small, and I'd rather not end up living in a fine metallic fog. So, time for some testing. Just how badly does this little grinder fling its dust across the room? A few simple tests should give a first impression. I weigh a piece of steel, grind off exactly 1 gram in a clean environment, and then sweep the area with my magnetic pickup stick. I weigh the collected steel dust. Then I weigh all the dust on the machine's exterior. And finally, I check how much has ended up inside the machine itself. Of course, the big question is, how much dust seems to have disappeared? I repeat the test 3 times, once at low speed, once at higher speed, and once at high speed with the vacuum system connected. The graph shows the results. The results show that most of the dust ends up where it's supposed to be, in the collection bin at the bottom of the machine, or in the vacuum cleaner. It's also clear that the vacuum doesn't just keep the inside of the grinder clean. It significantly reduces the amount of dust on the outside of the machine and in the surrounding area as well. The roughly 3% of dust that goes missing at higher speeds is still a bit of a concern. I'll see if there's a way to improve that further. So far, the build is actually going surprisingly well. The machine runs smoothly, and the speed is easily adjustable across a wide range from 200 to 7,000 RPM. I've already started tinkering with a mock-up for the design of the cross slide. One thing is absolutely clear. The two linear bearings must be mounted in such a way that none of that fine grinding dust can ever find its way between those tiny bearing balls and precision surfaces. That would be a nightmare. Balancing the drive wheel at the beginning of this video has clearly paid off. I can now crank up the speed to a ridiculous 7,000 RPM. That's equivalent to 132 kilometers per hour, without the machine vibrating annoyingly. And that's it for now. Next time, which will take a bit longer due to my holiday, I hope to start working on the cross slide. And if all goes well, I might even be able to share some first results on its precision. Thanks for watching. Hope to see you next video.